Morning, everybody. Let's start off with showing you a short demonstration. I'll go ahead and move my computer screen so you can see it. I'm going to show you beakers at different temperatures and their effect. I'm going to get out a beaker from the fridge. So the fridge is about 34 degrees or so. It's just right about it. Then I have room temperature water, and I have boiling water. Okay. Hopefully you can all see that. Let me move this over just a little bit more. So what I'm going to do is I'm going to add dyes to each of these and see the difference in how the dye moves through the different temperature water. So I have hot water I'm going to start with. And this is methyl violet. It's used in biology to stain bacteria. Okay, so this is hot water, and you can see that already it's turning purple. Room temperature water and cold water. So you can see a dramatic difference in how the dye disperses. 212 degree Fahrenheit water, it's right at boiling. Room temperature water, about 66 degrees. And then water from the fridge, about 34 degrees. So you can see in the middle one, now the dye is starting to disperse, but in the 212 degree Fahrenheit one, it's already all purple. And then in the cold water, it's not moving at all. So you can think of temperature as the relative motion of atoms. With a higher temperature, atoms move faster. And that's why in the hot temperature water, the dye disperses throughout the entire volume. Because the atoms in the water are moving a lot faster with a higher temperature than they are in a cooler temperature. And when they move faster, they can move the dye throughout the water. But you can see right here, room temperature water now, it's mostly purple with 34 degree temperature water. Starting to move a little bit, but still not very much. So this shows two things. Einstein used this to show that atoms exist. You know, he said that the motion of the dye through water shows that there must be atoms. There must be particles that move things around for this to work. And with a higher temperature, we can see faster motion, which must mean that atoms move faster at higher temperatures. We go move out of the way and we'll start the lesson today. We're in chapter 12 now, and we'll go through a little bit of chapter 12 today. Let's get this set up. Okay, so the main thing I want to talk about today is temperature and what that represents. We've got the whiteboard pulled up on here. So you can think of temperature in this way, that temperature is the average kinetic energy of the atoms in a sample. So it's an average, which means that with any substance you have, let's say that we have room temperature water. Let me draw that. So this water is at 72 degrees Fahrenheit. That's its average temperature. That's the average temperature of all the atoms in the water. Now, there are trillions and trillions of atoms though in the water. So averages indicate that there will be numbers above and numbers below this temperature. Some atoms in here will be at 212 degrees Fahrenheit. And they will jump out of the water. Some will be a lot lower than 72. Some might be at, say, 32 degrees Fahrenheit. And there'll be a lot in between. Now, of course, the average is 72. So most atoms are going to be at 72 degrees or close to that temperature, but there definitely are atoms that are well above that temperature and well below that temperature. And again, remember what temperature represents. It means the speed. And so that's really all we're saying, is that some atoms are going at a speed of 212 degrees Fahrenheit, which means they'll be able to jump out of the water, because that's the boiling point of water. Others will be at 32 degrees Fahrenheit, which means they'll be mostly stopped. They're going to, at 32 degrees Fahrenheit, when they become solid, they just vibrate in place. They don't really move very much. So some won't have very much movement, while others will have a lot of movement. And that's what we mean by temperature. But the majority of them will be around 72 degrees Fahrenheit if that's the temperature of the substance. But just remember that it's an average, and for individual atoms, you're going to have some that are well above and some that are well below that average. Let's look at temperature scales. There's Celsius. We'll start with that one. In 1741, Anders Celsius invented the Celsius scale. And what he said is that 0 degrees Celsius is the freezing point of water. And then 100 degrees Celsius is water's boiling point. And so he devised a temperature scale where he just said, okay, well, this is 100 degrees when water boils. This is 0 degrees when water freezes. And he'll just make 100 tick marks in between 0 to 100 to get 1 degree Celsius. So that's what his scale is based off of, the boiling point and freezing point of water. There's two other scales. There's the Fahrenheit scale and the Kelvin scale. So for most of the world, besides the United States, they use Celsius to measure temperature, but we use Fahrenheit for our weather reports. But even over here, scientists will use Celsius in the laboratory. So Celsius is the preferred unit of temperature in the laboratory for chemists. Now, physicists, though, usually they use Kelvin. The other scale is Fahrenheit, and that's more arbitrary than Celsius is. Fahrenheit is really based off 0 degrees Fahrenheit, which was just the coldest thing that he could make at the time. Fahrenheit made this ice and salt mixture. And you might have heard about this before, that if you add salt and ice, you can get a very cold temperature. You can get negative 15 degrees or so. It depends on, what you can, how much you add of the salt and the ice, but you can get into the single digits or even below 0. So salt lowers ice's freezing point quite a bit. You can get down to the negative values or single digits. Now for Fahrenheit, though, in the laboratory, 0 Fahrenheit was the coldest temperature he could reach by making this ice and salt mixture. So it was the coldest substance that he encountered. Now, of course, we can get temperatures much lower than 0 degrees Fahrenheit. You can go to even Minnesota, Wyoming, northern states will get much lower than 0 degrees Fahrenheit every winter. But for Fahrenheit, that was the coldest temperature he experienced. And so that's what he called 0 Fahrenheit. And that's really it. That's what he based it off of. 100 degrees Fahrenheit doesn't really mean anything. It's a hot temperature, but he didn't make that off anything. It was just 0 degrees Fahrenheit that he based a scale off of. So while it's arbitrary, what is nice about this scale is that they are very low degree differences. 1 degree Celsius is equal to 1.8 degrees Fahrenheit, which means that if you jump up 1 degree Celsius, you jumped about 2 degrees Fahrenheit. So 20 degrees Celsius is equal to about 68 degrees Fahrenheit. But if you go up to 21 degrees Celsius, you've now gone up 2 degrees Fahrenheit to about 70 degrees. So you do get a more precise measurement with Fahrenheit because you can go in between these numbers. So you can get a better idea of what the temperature feels like because Fahrenheit has a smaller scale. But besides that, Fahrenheit's not a very accurate or very useful scale because it's not really based on anything that's useful for a scientist. Kelvin by far is the most useful temperature scale for physicists and chemists. It's based off absolute zero. So 0 Kelvin is absolute zero. And it's the coldest possible temperature in the universe. So it's not the coldest temperature on Earth, it's the coldest temperature in the universe that's possible. And so nothing can get below 0 Kelvin. So that's when there's no motion, no thermal energy, all atoms stop moving. So you can't get below that. At that temperature, there's no energy. You can't get below 0 energy. Zero Kelvin is equal to negative 273.15 degrees Celsius, which is equal to negative 459 degrees Fahrenheit. Now here on Earth, we might get about 80 below 0 Fahrenheit in Antarctica, but that's about the coldest we'll ever get here on Earth. In space, though, it gets pretty close to absolute zero. You know, it really gets to be 2, 3 Kelvin in space. But here on Earth, we're far away from absolute zero. So a few equations you should know to convert between temperature scales. The first one, converting between Celsius and Kelvin. So to go from Kelvin to Celsius and vice versa, you would take Celsius and add 273.15. And that will give you the temperature in Kelvin. So for example, 20 degrees Celsius is about 70 degrees or so Fahrenheit. To convert Celsius to Kelvin, you would just add 273.15 to that. So Kelvin would equal 20 degrees Celsius plus 273.15. And that equals 293.15 Kelvin. So very easy conversion, and just you can go the other way too. If you were at, say 77 Kelvin, which is what liquid nitrogen is at. And you wanted to go from Kelvin to Celsius, then you would just go the reverse. You would just subtract. So we'll put in 77 Kelvin in for K. We don't know Celsius, so that's the unknown, plus 273.15. Subtract it. And that'll give you your answer in Celsius. So would that equal, let me see really fast. You do 77 minus 273.15. And that gives you negative 196.15 degrees Celsius. So Celsius and Fahrenheit can be negative, but Kelvin will never be negative because 0 is the coldest temperature you can ever have. Okay, so that would be how to convert between Kelvin and Celsius. I'll show you how to convert between Celsius and Fahrenheit. Okay, so for that equation, if you want to go from Fahrenheit to Celsius, you would use this. Fahrenheit equals 9/5 times Celsius plus 32. And the other equation, Celsius equals Fahrenheit minus 32 multiplied by 5/9. Okay, so let's go through an example with this. Let's say you wanted to know 100 degrees Fahrenheit to Celsius. So we're given Fahrenheit, we want to find Celsius. We'll use the second equation to do that. So whatever we're given should be in the equation. Whatever we want to find should be isolated on the left-hand side.
Wait, Miss Holly, do you use the little degree symbol on Kelvin or no?
Oh yeah, good question. No, you don't. Yeah, so you don't ever say degrees Kelvin, only Celsius and Fahrenheit, but Kelvin you don't.
Okay, thank you.
So you just do that, 100 minus 32 times 5/9, and that would give you 38 degrees Celsius. So that's how you convert between the two. So that's all we'll be doing today for the lesson. We'll talk more about this section for the next few days. But for homework today, I want you to work on page 317. Just do 1 and 2 on page 317.